This is part 2 of 3 of chapter 10, which is titled Acid-Base Titrations. Let's get started. Starting with section 10.2, it's titled Titration of a Weak Acid with a Strong Base. If you read the first sentence of this section, it says the titration of a weak acid with a strong base puts all of our knowledge of acid-base chemistry to work. This is going to be very tedious, so you have to really keep clear what section of the titration you're in if you're going to get this correct. So there's 4 regions to a problem like this. Okay, the first one is, of course, before any base is added. Solution just has HA in it, which is just a weak acid. Okay, it's a weak acid problem, and the pH is determined by the equilibrium that we've seen before for weak acid reactions. The second part of a weak acid with strong base titration is from that first drop of strong base that you add until immediately before the equilibrium point, there's a mixture of unreacted weak acid plus whatever conjugate base that's produced. If that should remind you, it's exactly like a buffer. So what we'll use is the HH equation to find the pH. The third region is at the equivalence point, which basically is when all of the weak acid has been converted to that conjugate base, A-. So the problem at this point is the same as if the solution had been made by dissolving a weak base in water. And the problem is determined by the reaction that you see here below, which is adding water to a conjugate base. The fourth and final portion of this type of titration is after the equivalence point. And of course, if you're reacting a weak acid with a strong base, after the equivalence point, you're going to have excess base, strong base there. And you're adding that to a solution of weak base. So whenever you're adding a strong base to a weak base, you can pretty much assume that everything is dominated by that strong base. So you calculate the pH as if you had simply added excess NaOH to the water. And we ignore that little effect, that small effect of the weak base, because really it's all dominated by that strong base. As a summary, the first portion is a weak acid problem. The second portion is just a buffer. So you use your HH equation to find the pH. The third portion is just a weak base problem. And the fourth portion is just when an excess strong base is added to water. So it's basically dominated by the amount of strong base that's added. Let's go ahead and do a problem so we can kind of get accustomed to how these things go. All right, so region 1, before base is added. Anytime you do any type of titration problem, the first thing you should do is figure out what the equivalence point is. So let's say that we're titrating 50 mils of 0.02000 molar MES. Now MES is just an abbreviation for 2N-morpholinoethane sulfonic acid. Would never remember that, but that is a weak acid, and I've told you there, you could see it because I've put HA. So 50 mils of this weak acid, and you're titrating it with 0.1 molar sodium hydroxide. If you set it up, basically to figure out the equivalence point, you would take 50 mils times 0.02 and then divide by 0.1, which is the molarity of the base. You'll see that the equivalence point is 10 mils. So now you know that is the equivalence point. Great. Let's find out what the pH is before we add any base. Before we add any base, you have 0.02 molar of this weak acid. And they gave you the pKa. I didn't mention that before, but in the book, you'll see that they give you the pKa of MES, which happens to be 6.27. So to find the pH is just how we've done it before back in chapter 6 when we were working with weak acid, weak base problems. So the equilibrium expression is going to be x squared divided by F minus x, where F is your formal concentration, of course being 0.02000 molar. And you know your Ka because they gave you the pKa. So all you would do is solve for x. This, of course, entails you to do the quadratic equation. I'm not going to go over that in this video. We went over that back in chapter 6. So if you do all of that, and I encourage you to actually do the calculations to make sure you get the same answer they get, you'll see that you get x is equal to 1.03 times 10 to the negative 4th. That is your concentration of H+. So you can go ahead and convert that to pH directly by the negative log of H plus equals your pH, which you'll get 3.99. Region 1 dominated by the weak acid dissociation. So you just find the pH as we've done normally before. Region number 2. This is also should be pretty simple because we've done buffers already. But before the equivalence point, after the first drop of base has been added, now we have a buffer. Because we started with a weak acid problem and now we're adding some strong base. Remember that any addition of a strong base is going to be immediately converted to A minus, that weak base conjugate. So let's consider a point where we're adding 3 mils of strong base. So we set up our little table just like we did before with our buffers, and before you find out what you're starting with, realize that you have to write down the equation so you know what to actually look for. The equation here is your weak acid and you're adding strong base to it. So it's HA plus OH is going to be converted to that weak base conjugate plus the water. Now initially, how many moles of HA do you have? Well, we started with 50 mils of a 0.0200 molar MES. If you multiply those two together, of course converting milliliters to liters, you'll get 0.001 moles of HA. You're adding 3 mils of that strong base. The strong base, remember the concentration was 0.1, so 0.003 times 0.1 is going to give you 0.0003. So that's how many moles of OH you're adding. Now, finally, after that is done, obviously you're not going to have all of the HA that you started with. So you have to subtract 0.0003 from 0.001, which gives you 0.0007. Finally, you're not going to have any OH left because it's all going to be consumed and turned into the weak base conjugate. We have our fraction, we have our quotient that we can use to plug into the HH equation and find our pH. We know the pKa, they gave it to us, 6.27, plus the log of A minus 0.0003 divided by 0.0007 equals 5.90. So you can do at any volume that I give you before the equivalence point and after the first drop of that strong base has been added, you can use the HH equation to find out what the pH is. What about region number 3? That's the equivalence point. At this point, the quantity of strong base is exactly enough to consume all of that weak acid. We know how many moles everybody has at this point because all we got to do is multiply the amount of volume times their molarity. And if you set up your little reaction, it's the same thing. HA plus OH is going to the weak base conjugate plus the water. How many moles of HA did you initially start with? The same. How many moles of strong base have you added? Well, it's 10 mils. 10 mils times 0.1 is going to give you 0.001. Finally, you're not going to have any HA left because all of it has been consumed. You're not going to have any OH left because all of it's been consumed and been converted to that weak base. And that's how much weak base finally you're going to have. So all this is really a weak base problem. So you do the same thing that you did before for region 1, but now it's a weak base. So it's the opposite, right? So we have the reaction of a base and you react it with water. So your A minus plus water, conjugate base plus water, is going to be converted to HA plus OH. But remembering now that since this is a weak base, you have to convert that Ka to Kb. If you take your pKa, which was 6.27, you convert that to Ka, which of course would mean to raise 10 to the negative 6.27, that'll give you 5.37 times 10 to the negative 7th. But then if you convert that to Kb, you should get what you see on the screen here, 1.86 times 10 to the negative 8th. You set up your Kb expression. The only thing is that the formal concentration is not exactly what you started. It's no longer 0.0200 molar because we diluted it. Remember, we've added 10 mils of a strong base, which was exactly what it took to get to the equivalence point. So that formal concentration is not the same. So how do we figure out the formal concentration now? At this point, you would take how many moles of weak base was created, which was 0.001, we just calculated that, divided by the volume of the solution, which is now 60 mils, because we've reached the equivalence point, which was 10 mils. 50 plus 10 is 60. So that is now your formal concentration, which is 0.01667. So now we can plug into our Kb equilibrium expression and get our pH. So we would have 1.86 times 10 to the negative 8th is equal to, of course, your HA times your OH divided by your A minus. That's, of course, the x squared F prime minus x. If you calculate all of that and you do the quadratic equation, you should get 1.76 times 10 to the negative 5 molar. Remembering that is your concentration of OH. I want the pH, so I can take the negative log of Kw, 1.0 times 10 to the negative 14th divided by my x, and that'll give me my pH. Remember, the equivalence point pH of a weak acid with strong base titration will always be greater than 7. I know I've put less than 7, that's a misprint. I should have put greater than, but because remember, you're adding strong base to a weak acid, so the equivalence point is it's never going to be 7. That's only if you have strong acid and strong base. It's always going to be above 7. I mean, because all of the acid is being converted to its conjugate base at the equivalence point. All right, so what's the last region? It's after the equivalence point. This is simple too, because all we're doing is we're adding a strong base to a weak base. And like I said before, the NaOH is so much stronger than that weak base that a fair approximation to say that the pH is really just determined by that strong base, the excess strong base. So for example, let's calculate the pH when the volume of base that has been added is 10.10 mils, which is 0.10 mils after the equivalence point, which is 0.00010 liters times the molarity of the base, which is 0.1. If you multiply that, you should get 1 times 10 to the negative 5 moles of OH. To find out the concentration of OH, you just take the moles divided by the total volume, and that should give you 1.66 times 10 to the negative 4th molar. To find out the pH here, all you got to do is convert that, which is your OH concentration, convert it to H concentration, and take the negative log, and you will get 10.22. So we have done all 4 regions of a weak acid with a strong base titration. The region number 1, it's just a weak acid problem, and we've done these many times. Region number 2, the minute that you start adding base to that weak acid, that's a buffer. So you use the HH equation. Region number 3 is the equivalence point, and that is simply a weak base problem. The only tricky point, remember, is that the formal concentration that you use in your equilibrium expression, x squared divided by F minus x, that F is really F prime, because it's not going to be the same concentration that you started at the beginning because you've diluted it. But region 4 is after the equivalence point, which is dominated by the strong base. If you can keep those 4 regions separate and clear in your brain, then you've got this. So this is showing you the titration curve of a weak acid with a strong base. There's really 2 identifiable spots in a graph like this. The first one is, of course, the equivalence point, which is the steepest part of the graph, that you're going to have the greatest change in pH around that equivalence point. The second identifiable spot is half the volume that it takes to get to the equivalence point. See here, the equivalence point was 10 mils. Half of that is 5 mils. At that half is when your pH is equal to your pKa. That is the area with the minimum slope. It's basically where the pH does not change that much when you add strong base. And another way of saying that is that's your buffer capacity. Remember, we learned about buffer capacity. This is a very useful graph, and you got to make sure that you understand how to read these graphs and that you know how to define the certain parts of the graph. All right, guys, that's it for this video. I am going to resume with part 3, which is the last part of titrations. See you guys later.